Okay, hello. So this is this is another episode in the series of step questions, showing you how to do step questions from Step Maths, and I'll get straight on with it. So you see here we're talking about Step 2007, Paper 3, Question 8. So the question is rather long, so I've split it into two screens. The first part of the question, part 1, is here. So if you want to do the question before you watch the rest of the video, you can look at part 1 here, pause the video and look at that, and also part 2 is here. So again, if you like, you can pause the video and look at that when you want to. Okay. So let's talk about the question now. Let's first of all observe the topic. The topic is differential equations, and so differential equations. Now, of course, you can look at the specification document, which is like the syllabus, if you want to double check what knowledge is expected on this topic in step. Excuse me, but basically the knowledge expected is exactly the same as what you should have learned in further maths. So further pure maths, you would have learned about I guess a couple of things. The general second order linear differential equation. So let me just this is by the side of the actual question, but just about prior knowledge. The general second order linear differential equation, we would be looking at something like this: a times d2y by dx squared plus b dy by dx plus cy. Now this could be equal to some function of x, or it could be equal to 0, and this is called the homogeneous case. So it's a bit of a technical word, that homogeneous, or homogeneous if you prefer. But you should definitely have already learned how to solve this case, this equals 0, and also this equal to fx, using the homogeneous case as a sort of subset of the solution set. So obviously I'm not going to go into details on how we do that, but I want to also mention that another thing that you should have learned or looked at is the idea of what should I put here? Maybe that's not a good idea. Something like a substitution is what I'm trying to get at. Substitution, where we change the variable of the differential equation and rewrite the differential equation. So you can sometimes solve a differential equation by changing the variable, making a substitution, and creating a new differential equation which you know the solution to. Okay, so those ideas are vaguely, and I won't be too specific, but those ideas are going to be useful in this question. And if you haven't studied the topic on differential equations in further pure maths, then you almost certainly won't be able to do this question. Now then, so from now on I'm going to assume you know you have that knowledge. So let's look at the question itself. Find functions a and b such that these two functions, u equals x and u equals e to the minus x, both satisfy this differential equation here. And then it says for these functions a and b, so you should have found these functions, write the general solution of this equation. And then it says show that this substitution transforms this equation into this equation. So although this takes up a lot of space, is actually quite a small part of the question, because they're telling you exactly what to do here. And from that knowledge show that the solution of star, so this equation here, that satisfies y equals 0, x equals 0 is given by this. Okay, so this first part is, I would say most of it's quite easy, but there's maybe one little idea that a lot of people I think would struggle with. So let's start at the beginning. We need to find functions a and b such that these two functions are solutions to this equation. So let's write the equation first. The equation is d2u by dx squared plus a of x, so a as a function of x times du by dx, plus b function of x times u is equal to 0. That's our starting point. And I want you to observe that this is not of the form a with ABC constant. Yeah? So what you should have learned is that for this linear, homogeneous, second-order differential equation, the correct way to find the set of solutions is to look at the auxiliary equation. Let's say a, what do I say, a z squared plus c, bz plus c equals 0. The solutions to this will tell you the exponents of the functions that you're looking for. So that should be book knowledge. But it doesn't apply here because a and b are functions of x, they're not constants. Yeah? So that means we don't yet have a standardized way to find this, to find the solution for this. But we're given special knowledge in this case. U equals x solves, and u equals e to the minus x solves. So we can simply apply that to the equation. So if we start with u equals x, d2u by dx squared is 0, and du by dx is 1, and bx times x must be equal to 0. So this gives me something simple like a equals minus x bx or something like that. Well, let's just say a equals minus xb, that's less confusing to look at. So we could consider this as maybe equation 1. Now let's look at the second possibility, e to the minus x. So the second derivative of e to the minus x is e to the minus x. The first derivative of e to the minus x is minus e to the minus x. And then we have b of x times e to the minus x. So obviously e to the minus x cancels, giving me 1 minus a plus b equals 0. So that's equation 2. So if we combine these two, let me just create some more space, we're going to need it anyway. So if we combine equation 1 and 2, so because a is equal to b plus 1, so b plus 1 equals minus xb, so b is equal to, let me get this right, a plus, so what am I doing? B times 1 plus x equals minus 1, so b is equal to minus 1 over 1 plus x, and a is equal to 1 plus b, which is 1 minus x over 1 plus x, which is 1 plus x, so that's 1 over 1 plus x. So those are the correct formulas for a and b. Let's just write that down clearly. B of x is minus 1 over 1 plus x. A of x is 1 over 1 plus x. Did I get that right? Let's check the original. A and b, sorry, let me just double check that. Sorry, a is x over 1 plus x. That's a silly mistake there, because, yeah, sorry, silly mistake. Hope you spotted it. That should have been a 1 here, giving me x over 1 plus x. So a is x over 1 plus x. So let's put this all in a separate section there. So that's the first part of the question. Find functions a and b such that this is such that those satisfy this equation. For these functions, write down the general solution of the equation. Okay. So now we're considering the general. We're considering the particular differential equation d2u by dx squared plus ax, which is x over 1 plus x, times du by dx plus bx, which is minus 1 over 1 plus x, times u equals 0, has solutions u equals x and u equals e to the minus x. Now this is the part that I think some students might find unobvious, and I'm not sure how to explain it in a very simple way. I guess there's an element of trust involved. We have two solutions, two valid solutions. Now clearly, let's just stick with this here. Now clearly, if x is a solution, then ax is also a solution, and an important part of that is that the equation is homogeneous. You see, because it's homogeneous, well, that means that if I put ax in place of x here, here, and here, then the a will appear in each term, and so we're getting something like, well, so because this plus this plus this is 0 if u is x, then this plus this if u is ax becomes a times 0, which becomes 0. So ax is also a solution where a is any real number. And by the same logic, b e to the minus x is also a solution. Now, it's the other thing about linear differential equations. What's a linear differential equation? What defines a differential equation as linear? It means it's some combination, how to say that? Well, it means that the terms in the derivatives are how to say, are not powers. So it doesn't. This equation does not include things like du by dx squared or d2u by dx squared to the 5 over 2. Yeah, so it's linear in that sense. So don't confuse linear with order or degree. Or the order of the differential equation is the highest derivative. So here this is second order because the highest derivative is 2. So you can have differential equations which are, let's say, second or third order, but are not linear if they have powers of the derivatives. But because this differential equation is linear, it means that I think I'll show this in detail, even though it's not necessary for this question, because I think a lot of students might find this difficult. But if you have because linear, let's say that, because the differential equation is a linear differential equation, then if I have a solution alpha and I have a solution beta, then alpha plus beta will also be a solution. Alpha minus beta will also be a solution. 2 alpha plus beta will be a solution, and so on and so on. So linear combinations of solutions are also solutions. So in case that isn't obvious to you, I want to show you why it makes sense. Suppose we have a solution like this. Suppose u of x, remember u is a function of x, equals fx is a solution, and suppose u of x equals gx is also a solution. Well, if ux equals fx is a solution, then it's true that d2f by dx squared plus x over 1 plus x df by dx minus 1 over 1 plus x f equals 0, and it's also true that d2g by dx squared plus x over 1 plus x dg by dx minus 1 over 1 plus x g equals 0. So those two are both true. And then if we consider a new function, u of x equals fx plus gx, so consider ux equals fx plus gx. If we calculate the same form, d2 by dx squared f plus g plus x over 1 plus x d by dx f plus g minus 1 over 1 plus x f plus g, is this equal to 0? Well, you should see that it must be equal to 0 specifically because of the fact that we say that the differential operator is linear. So again, I'm going to create a bit more space. This is just background material. This is not part of the actual answer, so don't worry if this is looking a bit crazy. You see, the point is that if you look at, and I'll just highlight it in blue, if you look at this expression, because of the general fact that d by dx ax plus bx is always equal to d by dx ax plus d by dx bx, in other words, you can split sums of differentials. Another way to put it is that the sum of the differentials is equal to the differential of the sum. So because that's true, you can see that in this term here I can split this derivative, and the same is true for a second derivative. So I can rewrite all of this as d2f by dx squared plus x over 1 plus x df by dx excuse me minus 1 over 1 plus x f, and then add separately d2g by dx squared plus x over 1 plus x dg by dx minus 1 over 1 plus x g. And we know that both of these terms are 0. This is 0, this whole bracket here is 0, this whole bracket is 0, so this whole thing is 0. Okay, now that is, well, first let me apologize for the handwriting. Of course it's a mess because I'm just rushing. But also, the purpose of showing that was just to emphasize the idea of the linearity of a differential equation. Yeah? So this differential equation is linear and homogeneous. That means that if I have two solutions, so here the theoretical solutions were f and g, but the actual solutions we have are x and e to the minus x. So what I'm doing with this long calculation here is proving that if I take any linear combination of these two, such as 3x minus 4e to the minus x, or minus 7x plus e to the minus x, any linear combination of these two will also be a solution by this kind of argument here. Okay, so let's get rid of all this because it was only theoretical. So most good students would probably kind of figured this out already, I guess. It follows that ux, and I'll just use numbers, or in this, as I put in blue here, just constants, ax plus b e to the minus x is always a solution for any real a, b. I suppose actually any complex a and b as well, but we're not interested in complex numbers in this question, I think. Well, let's just say then for any a, b constants. Okay, so that's always going to be true. Now here's the trick though. What you should know is that a second order differential equation is effectively solved by two steps of integration. So because it's solved by two steps of integration, it has two free variables or two constants. And since this expression already has those two free variables, that means that there are no other free variables. So the general solution is exactly what I've just written down. So this is the general solution. Is the general solution of the given differential equation. And if you like, you can write because second order. So because it's second order, it has two free variables, yeah? And because we already found two linearly independent functions, that's actually a very important point, that if you had ax plus b, you know, that would be a bit silly, ax plus b times minus 3x, then they would not be linearly independent, they would be the same function. And linearly independent just means you can't, there is no identity like ax equals b to the minus x. That's impossible. Certainly you can solve that as an equation, but as an identity there's no such numbers. So those two functions are linearly independent, so a linear combination of them, linear combination means multiplying each of them by a real number and adding them together is the general solution. So if you find that a little tricky to understand, please do read a bit more in your textbook about how to solve second order differential equations. Somewhere towards the beginning of the explanation there should be material about that. But I should probably say no more about that because I've already gone too long on that. So it does actually say, I didn't notice this, it does actually say write down. I think that's kind of important because it's something that you can understand fairly easily, but it's a bit more difficult to prove it. So we're not trying to prove this, we're just writing it down. So ux equals ax plus be to the minus x is the general solution. Now we're on to this second part here. Show that the substitution transforms the equation and this given equation into this other equation. Now of course at this point you should be happy because you see that the equation that we're aiming for, so we're going from here to here, but the equation we're aiming for has this, and these are exactly the functions ax and bx which we've already found. So we can already see that if we do succeed in transforming this equation called star into this equation, then we will have found the general solution because we already found the general solution of this equation in the first part. So I hope that's clear. Right, let's perform the substitution. First let's write the equation dy by dx. So we're given the following equation, dy by dx. Oh, I have a bad memory. 3y squared? Yeah. Plus 3y squared plus x over 1 plus xy. And all of that's got to be equal to 1 over 3 times 1 plus x. Okay, and we're told to apply the substitution y equals 1 over 3u times du by dx. Let's just double check that. Y equals 1 over 3u times du by dx. So we're going to apply the substitution and create a new differential equation, and hopefully it has the right form. Okay, so in order to perform this substitution, in order to use this, we're going to have to find a formula for dy by dx. You see on the left there. So let's do that differentiation. Dy by dx using this formula. So now we have a product. This is 1 over 3u times du by dx. So I'll first differentiate 1 over 3u. That gives me minus 1 over 3u squared times du by dx plus sorry, what am I saying? Of course this is u, so we're differentiating with respect to u and then with respect to x. So d by dx 1 over 3u times du by dx plus 1 over 3u times, and this is the second derivative of u with respect to x. That's the derivative with respect to x of du by dx. Now this one has to be done using the chain rule, doesn't it? So d by dx 1 over 3u, that's d by du 1 over 3u, that's minus 1 over 3u squared, but times du by dx. And then we've got du by dx again, and then we've got 1 over 3u squared d2u, 3u, sorry, careful, 1 over 3u d2u by dx squared. So a little bit messy, but here we have the square of du by dx. Now apart from that term here, let's using blue, apart from that term, all the other terms with y are just y directly. So that means we can now rewrite this whole expression using u instead of y, hopefully. So I'll just do it here. dy by dx, that's minus 1 over 3u squared du by dx all squared plus 1 over 3u d2u by dx squared plus, now we're going to go to this term here, 3y squared, that's 3 times 1 over 3u du by dx all squared, that's y squared, plus x over 1 plus x times y is equal to 1 over 3u du by dx. And on the right hand side we still have 1 over 3 1 plus x, no change there. Okay, so just need a bit of tidying up here. So we see, and of course this is the point, that this term with du by dx squared minus 1 over 3u squared is exactly cancelling with this term, because this 3 will cancel with one of these 3's, which are squared, and then we've got 1 over u squared du by dx squared. So this entire term cancels with this entire term, and then everything else will simplify down. So therefore 1 over 3u d2u by dx squared, what am I doing now, plus x over 1 plus x, so let's put a 3 there and a u there, du by dx, and let's take this over from the other side, minus 1 over 3 1 plus x equals 0. So multiply by 3u gives me d2u by dx squared plus x over 1 plus x du by dx minus 1 over 1 plus x u equals 0 as required. So that is exactly the same differential equation as we considered in the first part. So we've shown that this is transformed into this with the application of this substitution. So the only thing to be a bit careful about there is applying the chain rule properly, and it works out. Okay, and hence, so using that knowledge, show that the solution of star that satisfies 0, 0 is given by this. So we're going to find the particular solution. Maybe I should emphasize that. The particular solution of star with this boundary condition, or this initial condition, looks like that exactly. Okay. So we know the general solution of this equation in terms of u. So this has general solution what was the general solution? U of x equals a times x plus b times e to the minus x. Remember, two free variables, two linearly independent solution functions. But we know that y is equal to 1 over 3u times du by dx. So in order to make this calculation, we need to find du by dx. Well, du by dx in general will be a times 1 minus b e to the minus x. So therefore y, the general solution for y, will be what is this? Du by, so a minus b e to the minus x over 3 times the original u form here, ax plus b e to the minus x. And we know that when x is 0, y is also 0, and that should be equal to a minus b e to the minus 0 over, well, it doesn't matter, does it, but I'll put it anyway, 0 plus b. So if this is 0, well, it follows that a is equal to b. And okay, I've nearly finished, so I'll just shift this down a tad. Okay, so a is equal to b, so we simply substitute that fact into this form for y, and we see that y is equal to, let's say, a minus a e to the minus x over 3 ax plus a e to the minus x. So the a's actually cancel out, and we get 1 minus e to the minus x over 3 x plus e to the minus x. And that, I believe, was what we were to show. If we look back, yeah, we see here the correct form. So there's an interesting little point about this question, which I've actually only just noticed. Remember, I made a big deal about the fact that the first differential equation we looked at was second order, so it had two free variables, two free variables because of the second derivative here. Now this equation is first order. It's first order because it only contains the first derivative of y, not the second derivative. So it's interesting how this transformation that we perform, we change this first order differential equation into a second order differential equation. And it's easy to imagine that might be a bit of a strange thing to do, because this should have one free variable. Yeah? So in the sense that to find the function which satisfies this relationship requires one integration, and therefore one integration constant, or one free variable. But this has two free variables. But as we saw in the process, we only needed one boundary condition to find the single free variable for this equation. And as it turned out, the reason for that was because that one variable, that one boundary condition gave us a relationship between a and b, such that actually we were able to cancel out a in the final answer and just get a specific particular solution. Anyway, now the last part of the question is very, very typical. It's a classic kind of step moment, is that they say, okay, you've followed our rules, you've followed our instructions, you've found the solution for one thing. Now we're going to give you a slightly different equation. So here's the slightly different equation. So for comparison, let me show on the screen at the same time both of the equations. I might have to do some clever copying here. Yeah. So the equation that we've just solved was this one here. I'm going to copy that onto the same screen, maybe sort of here or something, if that's possible. Yeah, so that was the equation we just solved. Get rid of these blue marks. So we want to understand how what we just did can be repeated, or how does it have to be changed? Well, obviously there are two basic differences between this original case and this new case. The first obvious difference is the number 3 here is not appearing here. This is just a 1, not a 3. There is actually another difference, but that's a bit less obvious what's going on there, which is that we've got a plus in the original and we've got a minus in the new version. Apart from those two differences, it is the same. Yeah? Oh, of course, the 3 appears here as well. Now, when we look at, so we ask ourselves, can I repeat the same process to get the answer? So I've got a first order differential equation. Can I make a similar transformation into a second order differential equation which I already know the answer for? Well, there's going to be at least an element of guesswork about this. Let's remind ourselves, how did we do the first one? We used this substitution. Let's copy it again. We used a particular substitution, and it helped to do the job. Can we use the same substitution? Well, the first thought that should spring to your mind is that because there was a 3 in the original which has now disappeared, then probably we don't need this 3. And as it turns out, that is indeed the right thing to do. So we're going to change the substitution so there's no 3. And if you wanted to, you could just scan back, with your eyes over your previous working, and you could see, well, look, when I did my my transformation, my substitution process before, if I look at this line, if there's no 3, well, that 3 is going to disappear, that 3 is going to disappear, that 3 and 3 is going to disappear. Yeah, so you can see that the 3 was there in the substitution to take account of that 3. So we're not going to need it. So let's try and do it without that 3. Having done that, we're going to get a form which still won't be quite right, because we'll have these minus signs here. And you might want to think about, how can I deal with that? But in any case, you're forced to make an effort to just try and see if something will work. So let's try this substitution. Let's calculate what dy by dx is here. Well, as before, we'll need the product rule and the chain rule. So it will be d by du of 1 over u times du by dx times this du by dx again. Remember, I'm applying the product rule and the chain rule here, and then 1 over u, and it will be d2u by dx squared. So if I plug this formula into this expression, I'm getting minus 1 over u squared du by dx all squared plus 1 over u d2u by dx squared. So there's our second derivative. Now I'm going to take the square of y, which is 1 over u du by dx all squared. I mean, you can already see that it's going to work, isn't it? Because that term will cancel with that term. Now let's just do the remainder here. X over 1 minus x, y. Now y is 1 over u du by dx. And I'll just subtract the right-hand side. Minus 1 over 1 minus x. That's it. Equal to 0. So as before, this term cancels with this term. Multiply by u, and I get d2u by dx squared so multiplying by u, that will cancel the u here, plus x over 1 minus x du by dx minus u over 1 minus x. Did I get that right? Minus u over 1, yeah. So let's just say minus 1 over 1 minus x u, yeah, equals 0. Okay, so this equation that we've got from the substitution, from this substitution, looks different in one particular way, which is that instead of 1 plus x, we have 1 minus x here and here. So quick reminder, the thing that we worked out at the beginning was this one here, and it had 1 plus x in the denominator in both cases. But apart from that, it's exactly the same. Hold on, is that true? Plus, minus, plus x over 1 plus x, plus, minus, yeah. That's the only difference. Okay. So sorry if this is a bit difficult to follow. I mean, it will be easier if you've already tried the question yourself, of course. Okay, so how do we deal with this minus? Well, if you've got any equation where you want plus x appearing, but you seem to have minus x appearing, the most obvious thing to try is to say, well, suppose I made a new variable which was minus x. Then in that case, x over 1 minus x would become minus x over 1 plus x. And of course 1 over 1 minus x becomes 1 over 1 plus x. Now at first sight it might seem like that doesn't work, because you're thinking, well, the problem with that is that the this x in the denominator here has got a minus sign attached. We don't want to change this sign. This plus sign is already correct. So is that a problem? Well, it isn't a problem, because don't forget, if we're changing the variable, we've also got to change the derivatives. For example, du by d capital X is not the same as du by d little x. It's du by d little x times d little x by d capital X. Now this quantity, dx by dx here, this is just minus 1, isn't it? So du by d capital X is minus minus du by dx. Okay, so that means that this term, when we make this new substitution, this first derivative term will change sign, and that will cancel with this sign. Now, a similar logic would allow us to calculate d2u by d capital X squared. Well, that's d by d capital X du by d capital X, yeah? Yeah, that's right. And we already know that that's d by d capital X. We know that this term inside the brackets we calculated here is minus du by d little x. Well, now we can apply the chain rule again. That's d by d little x minus du by d little x times d little x by d capital X. And as we know, again, that's minus 1. So we get a minus 1 and a minus 1. So we get no change in sign. Dx squared. There we go. So that might be obvious. Maybe there's a more obvious way to observe that fact, but I'm just going to be very specific here. So if I apply this substitution right across the whole of this equation, right across the whole of this differential equation here, term by term, this is what happens. Let's actually make a copy of this. It'll be easier. There we go. So we'll make a copy of this and apply these facts that we've just observed. Okay. So term by term, the second derivative is unchanged. Oops, there we are. The second derivative, d2u by d capital X squared, is exactly the same as d2u by d little x squared. Now, x over 1 minus x, well, that was minus capital X over 1 plus capital X, and du by dx was minus du by d capital X. And then minus 1 over 1 plus x, capital X, times u equals 0. And just rewriting the signs there gives me d2u by dx squared plus x over 1 plus x du by dx minus 1 over 1 plus x u equals 0. So finally here we have exactly the same form. If you observe carefully, that's exactly the same form as the original equation here, and therefore we already know the solution. So therefore u as a function of capital X is indeed a times capital X plus b times e to the minus capital X. And since capital X and little x have a simple relationship, I can use u of x is well, a of x, the a can be opposite sign, plus b e to the plus x, like that. Okay, so we know that the general solution in terms of x is u of x is ax plus b e to the minus x, but don't forget we had the substitution. The substitution was y equals 1 over u, no 3 this time, times du by dx. Well, du by dx is just a plus b e to the x. So therefore y equals that function, a plus b e to the x, over ax plus b e to the x. And now we apply y equals 2 when x equals 0, and we get 2 equals a plus b over a times 0 plus b. So we have 2b equals a. Sorry, just let me be a bit clearer. That should be 2b minus b, isn't it? Yeah, 2b minus b equals a. So a equals b. Now, just in case that was a bit confusing, I want to emphasize that when I changed from the capital X to the lowercase x, this a has changed, hasn't it? Because actually capital X is minus little x, so this would be like minus ax, but because it's just any real number anyway, it doesn't matter as long as we define it. You know, for example, you could put a2 there if you wanted, but so perhaps a little bit lazy of me there. But anyway, using this system, I've got a equals b, and so finally I've got y equals a plus a e to the x over ax plus b e to ax plus a e to the x. Anyway, the point is that the a's cancel, so y is equal to 1 plus e to the x over x plus e to the x, and that is the final solution, or the particular solution for the differential equation given. So, in summary, I would say the question was definitely one of the easier ones, but only under a specific condition, which is that if you understand what is going on in linear differential equations, the idea of the order of the linear differential equation corresponds to the number of free variables in the solution, so that in particular, if you already know n different linearly independent functions which solve the given differential equation, where n is the order of the differential equation, then automatically you already know the general solution. So that's what they're talking about here. Write down the general solution. The general solution is a linear combination of a linear combination of x and e to the minus x. If you understood that, I don't think the rest of the question is very difficult. Although, of course, I should mention, as I said, that this where's it gone? Here. This second part of the question is a very classic and very typical thing in STEP, which is that they take a similar equation to the first part, but they don't tell you how to solve it. They leave it up to you to figure out. So let me show you here, in particular this, that you should figure out that this is a similar but not the same substitution as in the first part in order to follow the same process. Okay, so I think I'll leave it there. Hopefully that was useful. Thank you very much.